Good morning, all the students.
Very much.
Yeah, I want maximum attendance today because we are going to discuss some important algorithms. Can you see the screen? Okay. So let's move on to our fifth lecture in this module 1. In the previous session, we have got the introduction to concept learning and how a concept learning task can be performed. For this, we have taken example of of your friend, whether he enjoys the water sport or not, given some climatic conditions, given some weather conditions. Okay, so on some particular days where the weather conditions are very friendly, your friend may enjoy the water sport. But in on some days when the weather conditions are extreme or little uncomfortable, then your friend may not enjoy that water sport. Okay, so there are instances of various days given, and each day's climatic conditions and whether your friend will enjoy the sport on the day or not is given. Okay, now the machine has to learn from those instances of training examples and have to predict properly whether your friend will enjoy a water sport given some weather conditions of a particular day that are not seen by the machine so far, right? So we have some parameters like sky, wind speed, forecast of the day, and whether he'll enjoy the sport or not. That is the outcome variable, right? So we have various days data, day 1, day 2, day 3, day 4 data is taken, right? All these are called as attributes, and this is called as the prediction or the outcome or the output, or simply we can call it as the label. Okay, we can give lots of names to that, or we can simply call it as the concept that is being learned by the machine. And remember, concept, if the concept is defined as whether your friend will enjoy the sport on a particular day, the machine is interested only in S examples, positive examples, right? So the concept of learning is whether your friend will enjoy the sport. Okay, so only if it is S, the machine will try to generalize on that hypothesis. Okay, now different days data is given, day 1, day 2, day 3, and day 4. These are all called as instances, x, small x. Okay, and all these together will form, this is called as instance x1, this is called as instance x2, this is called as instance x3, and this is called as instance x4. Okay, so these are all instances which are denoted by small x and a suffix to that. Suffix means this number 1, 2, 3, 4, what we are giving. Now all this set will form the instance set x. Each of these instances will denote one particular day's data. Now all these instances together will form the final set, that is x, capital X. That is called as set of instances. Okay, so you are quite comfortable with this terminology. Whenever I use all these terms hereafter in the classes, you should not be confused. When I say set of instances, I am referring to X, all the sample points. When I say small x, I am referring to each instance, each sample point. When I say attributes or features, I am referring to these column names. When I say label or concept or outcome or dependent variable, I am trying to refer to this y, that is the outcome. Okay, now all these terms are very clear to you. Let us proceed further. Today's concepts, we are going to learn about how concept learning is treated as a search problem and finding a maximally specific hypothesis by using the find S algorithm. This is a very important algorithm. It is like a game for you. Do not think that if I am introducing you to an algorithm, it is somewhat complex, or the terminologies or some mathematics will be underlying behind that. Do not worry, it is like a simple game. You will understand very easily. Just focus from the step, right from step 1 to last step. That's all. It is very easy to understand. Okay, now let us start with how concept learning task is treated as a search problem. Concept learning can be viewed as the task of searching through a large space of hypothesis implicitly defined by the hypothesis representation. Okay, so whenever a concept has to be learned, the machine has to search in the hypothesis space H, different hypotheses H1, H2, H3 and so on, and select the best hypothesis that will fit the training examples given, that will better explain all the combinations of the training examples given. Okay, so this can be treated as a search problem because you're trying to search from all the hypotheses available, which is the best hypothesis. You means machine here. Okay, the machine is trying to search from the hypothesis space, capital H, different hypotheses and select the best hypothesis that will fit the training examples. Got it? So this is called as this is defined by the hypothesis representation. Now the goal of this search is to find the hypothesis that best fits the training examples. Okay, that can better generalize to the future examples, to the unseen examples by the machine. Understood? The machine is learning from the training examples, and from the many hypotheses possible, it is selecting the best hypothesis, best solution that will better explain all the training example data. And now that hypothesis should also be generalizable so that it can predict in the same way with the same accuracy some unseen data also, some future data point also. Means in this enjoy sport task, you are given some previous day's data, a machine is given some previous day's data, and when the machine is given a new day's data, still it should be able to predict whether your friend will enjoy sport on the day or not, based on its experience that it has learned from the previous day's data, some 100 days data or some 200 days data. Here for simplicity only 4 days data is given, but actually in real scenario machine tries to learn from lots of training examples. Okay, now it is important to note that by selecting a hypothesis representation, the designer of the machine learning problem or of the machine learning algorithm implicitly defines the space of all hypotheses, that is your capital H, of all hypotheses that the problem can ever represent and therefore can ever learn. See here, the program can ever represent and therefore can ever learn. Means this hypothesis space will cover all the hypotheses possible, which will apply for each and every training example. And at each step, it will try to generalize because the machine can't always check all the hypotheses available when some new data point is given, right? So it tries to generalize. It tries to generalize on all the training examples and tries to minimize its hypothesis number and finally arrive at a final statement or final hypothesis which explains in general the behavior of the entire training set. Got it? So it is searching through a search space. It is searching through a space of hypothesis, through a hypothesis space, and finding the best solution among the alternative solutions available. Got it? Now, consider, for example, the instances X and the hypothesis space H in the enjoy sport learning task. So what are the instances available? 4 days data. And what are the hypothesis space? How many hypotheses will be there in the hypothesis space? Let us see how to calculate that. Okay, you're not going to calculate that in future, but I'm just explaining you how many possible instances can be generated by taking possible values under each attribute. Listen carefully. For example, the attribute sky, we have taken one attribute sky, that is your first attribute, first column in the enjoy sport learning task, has three possible values. Say rainy or stormy or windy or clear sky, like that. Take three possible examples. And for A, temperature, humidity, wind, water, and forecast, the other columns, each of them, let them have some two possible examples. Means A, temperature, high, low, humidity, high, low, wind, speed, slow. Like that, it may have some two possible values. Okay. Now the instance space instance space X contains exactly how many combinations? Three possible values for sky. So 3 into 2 possible values for A, temperature, and 2 possible values for every other column we have assumed. Okay. If these are the possible values, how many combinations you get? 96 distinct instances you get. Means 96 distinct training examples it can get. Maybe they are recorded really or not, we don't know, but most possible instances possible are 96. Okay, so what say if I take an attribute A and an attribute B, it has x1 and x2 as possible values. It has y1 and y2. So how many combinations you can make? 2 into 2. Total 4 combinations. X1, Y1, X1, Y2 is two combinations, and X2, Y1 and X2, Y2, two combinations, right? So total 4 combinations can be made. So 4 possible instances can be generated for this particular possible labels. Okay, in the same way, for sky, if there are 3 possible values, for A, temperature 2, humidity 2, and so on, total 96 distinct instances can be generated. But among that, we are given only 4 possible examples. Okay, 4 days data. For simplicity, we have taken very simple number. Okay, now let us take another example. Say sky has 5 possible values, and A, temperature has 4 possible values, humidity has 4 possible values. In that case, we can calculate that total 5120 syntactically distinct hypotheses within H. Means initially you will generate 5120 hypotheses, and the machine starts learning all those hypotheses and tries to combine the hypothesis, which can apply for some 10 examples as a whole, or another 10 examples as a whole, so that it will reduce into 512 hypotheses. Later it will reduce into 25 hypotheses. Later it will reduce into some 5 hypotheses, and finally arrive at a general hypothesis which will apply to all the training examples. Got it? Initially, there may be 5120 combinations of these attributes according to the number of categories it has. But slowly the machine tries to generalize it and finally arrive at a more general hypothesis. Got it? Now observe that every hypothesis contains one or more pi symbols representing the empty set of instances. Now it classifies every instance as negative. Consider in yesterday's class I have told, say there is one hypothesis where any value can be preferred, any value is allowed for all the attributes, but in that case every instance will be predicted as yes only, right? Because your friend is comfortable with any type of weather condition, he will enjoy the sport on any day. So his enjoying the sport, that is treated as S. Now consider another extreme case where your friend is not comfortable with any type of climatic condition. Maybe he doesn't enjoy water sport. That is for lighter side I'm telling. He is having water phobia. means given any day, given any climatic condition, on any day, he doesn't enjoy the water sport. That is most specific case, means pi. No value is allowed under that attribute. Here, question mark means any value is allowed under that attribute. Any climatic condition is okay for him. In this case, no climatic condition is okay for him. That is why we are representing it with pi, which will always be predicted as no, because he is not comfortable with any type of weather conditions. Got it? Now, observe that every hypothesis containing one or more pi, if at all in any hypothesis, no value is allowed for sky and no value is allowed for wind speed, and others can be anything. In that case, he is not comfortable with these two partial conditions. In that case, it will be a negative instance, right? He will not enjoy the water sport. It will be a negative instance. In that case, it classifies every instance as negative because the machine has not come across such examples. He is not comfortable with any climatic condition, means he is not comfortable as on the whole about playing a water sport on that particular day. So it classifies every instance as negative. Now, in that case, the number of semantically distinct hypotheses is remove that particular hypothesis which is having pi, and all the combinations of other attributes with that pi also have to be removed. So this becomes 4 instead of 5, this becomes 3 instead of 4, and so on. So the value will be total 973 distinct hypotheses. 973 distinct combinations after removing the pi. If pi is not present, if you have all valid combination, the total distinct hypothesis you get is 5120. Right? But if you are removing that one, that is any combination with pi, then you are getting the semantically distinct hypothesis as just 973. Okay, so whenever there are some pi involved, all those combinations can be removed because they will result as a no prediction, which is not interested by the machine in concept learning, because the machine is interested only in S examples, only positive examples. It is not interested in negative examples. Got it? Now, most practical learning tasks involve much larger, sometimes infinite hypothesis spaces. Now, if you take, say, characteristics of people in India, it is an infinite hypothesis space, right? Every person has different characteristic. Every person has different set of features. In that case, the hypothesis space will be infinite. Why? Because every person's characteristics, if you start combining, every time you'll get a unique combination. And that will result in almost infinite hypothesis space. Got it? Now, the machine has to search for some general characteristics of an Indian in that infinite hypothesis space. Is it possible? It is still possible, but it takes a lot of learning time. The machine requires a lot of learning time. Now, if we view learning as a search problem, if we take concept learning as a search problem, then it is natural that our study of learning algorithms will examine different strategies for searching the hypothesis space. Now, if the hypothesis space is very large, if the hypothesis space tends towards infinity, then what are the search strategies that have to be implemented in order to search that hypothesis space so that the machine will be able to select the best hypothesis that will explain all the training examples better. Let us see by taking help of some algorithms. Now, we'll be particularly interested in algorithms capable of efficiently searching very large and infinite hypothesis space, because this is a real life scenario. Though I am giving you during the class some simple examples, in real life, machines will try to learn from infinite hypothesis space. Remember, so you have to find out which are the algorithms that are very efficient in searching the best hypothesis from this infinite space. Okay, to find the hypothesis that best fit the training data. Now for this, there is an approach called as general to specific ordering of the hypothesis. Okay, you are taking two types, general to specific as well as specific to general. Okay, let us see how various algorithms take up these two kinds of approaches. Now, many algorithms for concept learning organize the search through the hypothesis space. Whenever I say hypothesis space, you should remember it as H, which is consisting of different hypotheses H1, H2, H3 and H4, each applying for your instances X1, X2, X3 and X4. Now, all these specific hypotheses should be generalized and the best hypothesis H has to be found out, which is in accordance with the concept C. Concept C is your problem statement. What is your problem statement in the previous case? Whether your friend will enjoy the water sport. That is the concept that has to be learned by the machine. So it has to find out a hypothesis which will better explain the training examples given, so that it can also tell whether your friend will enjoy the water sport on an unseen day by the machine. Fine, that is very clear to you. Now, many algorithms for concept learning organize the search through the hypothesis space as a general to specific ordering of hypothesis. Now, using this, we can design learning algorithms that exhaustively search. Exhaustively search means it will not leave even one particular example also. It will try to cover all the examples in the hypothesis space. Now, using this, we can design learning algorithms that exhaustively search even infinite hypothesis spaces, means very large hypothesis spaces, not actually infinite, but very large hypothesis spaces without explicitly enumerating every hypothesis. It need not give all the hypotheses to the machine, not required. It can combine those hypotheses so that some 10 hypotheses can cover one particular instance. 10 hypotheses can generalize one particular instance. Again, it will try to refine it and finally arrive at one single hypothesis which can apply all the training examples. See, in our previous case of playing checkers or playing chess, there we are finding the best optimal target function. We are having multiple equations, but among that you are finding the best equation that will match the purpose of the target function. In the same way, you are making a machine learn the best hypothesis that will help it to classify something. In this case, whether your friend will enjoy the sport, yes or no. Okay. Now let us consider the two hypotheses here, H1 and H2. Listen carefully from here. These are the stepping stones to understand your upcoming algorithm, that is FIND-S algorithm. So listen all these steps carefully. Let us consider two hypotheses. Very simple if you listen carefully. Okay. Let us consider the two hypotheses H1. Now this hypothesis H1 is, it can accept any instance with first value as Sunny and second instance any value it can be, third attribute value any value it can be, fourth attribute value maybe wind speed should be strong, and fifth and sixth attribute values can be anything again. Okay, this is your first hypothesis. Now what is your second hypothesis? This will accept all your instances of training examples where the first attribute value is Sunny and all the other attribute values can be anything. Okay, so this hypothesis will accept all such instances where the sky is sunny and other attribute values can be anything. It is very open. It can accept any values for other attributes. Now consider the set of instances that are classified positive by H1 and H2. Now wherever the sky is sunny and the wind speed is strong with any other possible combination of values, it will predict that your friend will enjoy the sport S. Okay, and in hypothesis 2, if the sky is sunny and any other possible combination of attributes with that, your friend will enjoy the sport. That is what is said by hypothesis 2. Now, because H2 imposes fewer constraints on the instance, it classifies more instances as positive. What did you understand from this? Say, I'll give a different example. Now, my hypothesis 1 is, I want a sweet which is the class is you excuse me. Yeah. Only one table. Sir, after the class. Sound, sir, sound disturbance. Okay, now let's get back. Because H2 imposes fewer constraints on the instance, it classifies more instances as positive. Yeah, where I'm trying to give an example here, right? So H1, if I'm taking as I want a food which is sweet and healthy also. Okay, I want a sweet which I want a food which is sweet as well as healthy. Okay, and my second hypothesis is I want a food which is sweet and I'm not bothered whether it is healthy or not. Which one, where I'm applying more constraints? In case of H2 or H1? Can anybody tell me? In which hypothesis I'm giving more conditions?
H1.
H1 or H2?
H1.
H1, exactly. We are giving more conditions that I want a food to be sweet as well as healthy. But in H2, I am giving lesser conditions, means I am more general about it. I want a sweet, but I'm not bothered about the condition that it should be healthy or not. Okay. In the same way, I'm taking here H1 is more specific because the wind speed also he is bothered about. But in H2, he is not that specific because he is bothered about the sky's condition only. He is not bothered about the wind speed. Now, what can you understand from this? Any instance classified positive by H1 will also be classified positive by H2, right? Therefore, we say that H2 is more general than H1. Simple understanding, right? That is what you already understood from this example I have given. Any instance classified positive by H1 will also be classified positive by H2. Do you agree with this? Did you understand this, students? So what do you say in this particular instance? H2 is more general than H1. My preference about a food, H2 is more general than H1. In case of H1, I'm more specific that it should be healthy. But in H2, I'm not that specific, right? So this is what we say that, this is where we say that H2 is more general than H1. Now let us understand this more general than relationship better. Now first, for any instance X, let us take one particular day's example in the instance set capital X, and hypothesis, one particular hypothesis let us take from the hypothesis space H. We say that X satisfies H if and only if H of X is equal to 1. What did you understand from this? We say that this particular instance or sample point satisfies this H only if it predicts a positive value, only if it predicts as S. only if it is in accordance with the concept. Got it? We now define the more general than or equal to relation. This is very important. This is indicated by this symbol, greater than or equal to, with a suffix as G. How do you normally call this? How do you normally specify this symbol? Greater than or equal to, right? But in this case, we are calling it as more general than or equal to by putting a suffix G here. Okay. Now we are trying to define more general than or equal to relation in terms of the sets of instances that satisfy the two hypotheses. Okay, so how we do that? Given hypothesis Hj and hypothesis Hk, Hj is more general than or equal to Hk if and only if any instance that satisfies Hk also satisfies Hj. So what I'm trying to tell here is, if you take Hj, in your previous case it is H2, is more general than or equal to Hk. Okay, that is H1. Means H2, whenever an instance is applicable, whenever an instance is applicable with for H1, then it will also be applicable for H2. Okay, this is what I'm trying to tell. If an instance satisfies this hypothesis H1, if it is sweet as well as healthy, then it satisfies the hypothesis that it is sweet. Okay, so H2 is more general than H1. That I'm putting it into a mathematical notation here. If I take Hj is more general than Hk, how do I represent that? Hj is more general than or equal to, I'm adding G here. You should not get confused between normal greater than or equal to symbol and more general than or equal to symbol. This is more general than or equal to symbol. Okay, so H2 is more general than or equal to H1. Now I'm putting this in more general terms. Hj is more general than or equal to Hk, because whatever instance satisfies Hk also satisfies Hj. Means Hj is general, Hk is more specific. H1 is general, H2 is more specific. Got it? Any doubt in this representation? Can anybody acknowledge on this? Did you understand? Or anybody who didn't understand can raise a doubt on this? Very simple representation, right? Do not get afraid seeing these mathematical notations. If you understand the underlying concept, this notation is nothing at all. You'll easily understand. Did you understand, students? Good. Now, if I say another hypothesis, HL is more general and HM is less general. Means HM is more specific, HL is less specific. How do you develop a relationship like this? Can anybody tell me? How can I write this relationship? HM is more specific. I'm telling it the other way. Do not get confused. I'm not using now general than, I'm using specific than. Okay. Now HM is more specific than HL. HM, I'm giving more conditions about the food. HL, I'm giving less conditions about the food. Now, which is more general?
HL.
HL is more general.
HL.
Yes. How can I write the relationship now? Can you read the relationship?
HL is
HL is
more general than or equal to HM.
HM. HL is more general than or equal to HM. Very good. You understood this. So I'm going to next part. Now let us define this relationship so that it is in a formal definition. Okay. Let Hj and Hk, understand carefully, let Hj and Hk be Boolean valued functions defined over the instance set X. Then Hj is more general than or equal to Hk, written as Hj with this symbol, more than general than or equal to Hk, if and only if. How do you represent this? For every instance that belongs to the instance set X, if more specific hypothesis is predicted as a positive example, it implies that, what is this symbol called as? Implies. It implies that Hj of X also should have been predicted as S. Got it? Because Hj is your more general description. Hk is your more specific description. In that case, if an instance is predicted as positive by Hj, surely it would, if an instance is predicted as positive by Hk, surely it would have been predicted as positive by Hj also. Why? Because that is more general representation. Okay, so this is the most essential representation in this case. Hj is more general than Hk. So what all instances that are applicable by Hk are also applicable by Hj. Got it? This is the definition for more general than relationship. Now, some playing with mathematics will do. Okay, Hj is greater than, more general than or equal to Hk. This you understood. Now, is Hk more general than or equal to Hj? Or I'll put it in other way, Hj is more general than, strictly more general than Hk, if I want to say. I'm repeating again. If Hj is strictly more general than Hk, means it is not equal to than Hk. In that case, how I can write? Hj is more general than or equal to Hk and Hk not more general than or equal to Hj. Got it? Means Hj can be general than Hk, but Hk will never be general than Hj, or it will not be even equal to Hj. Then we say that Hj is more strictly general than or strictly more general than Hk. Okay? This way is applicable. Vice versa is not true. Backwards direction it is not applicable. Okay? Hj is strictly more general than Hk. Why? Because Hk is not at all equal to or more general than Hj. Now how do I represent this? Hj more general than Hk. I am removing the equal to term. Did you notice? This says that Hj is strictly more general than Hk. Got it? Let us see in instances how it will be applicable there.
Excuse me. For not more general, same symbol, ma'am. There is no difference between.
Where?
Hk is not, you told Hk is not.
No, sorry. I have to strike this out. Okay. Now it is correct?
Yes, ma'am.
I forgot to strike this out. Hk is not general than or equal to Hj. In that case, we come up with this representation that Hj is strictly more general than Hk. Equal to we are removing. Now let us see this with an example. Now take the first instance x1 where certain climatic conditions are given: sunny, warm, high, strong, cool, and same. That is represented by, in the diagram, represented by x1. Okay. Now let us take another instance x2, sunny, warm, high, light, warm, same is given. That is represented by x2 in this diagram. Now how the hypothesis can be written? H1 from x1, we can make this hypothesis sunny and strong. It is let us keep it specific, and let these values be anything which are acceptable by your friend to enjoy the sport. That is why he is specific only with the sky condition and the wind speed. In other cases, he is not bothered. Whatever is the condition, he'll enjoy the sport. That is the first hypothesis, which will satisfy for which x1 will satisfy this hypothesis. Now, let us take this third instance, the third hypothesis, which is where x2 will satisfy this hypothesis, where your friend is bothered about the sky, that is sunny. He is okay with any other weather condition, and wind speed, the temperature maybe, it should be cool. And the last condition can be anything again. Okay, this is hypothesis H3. Now, he has more general expectation, means he is only bothered about the sky condition, sunny, and he is okay with any other combination. That is H2. Now tell me which is more general. Can you make two mathematical expressions?
H2, ma'am.
H2 is more general than?
H1 and H3.
H1 and H3.
Very good. Who is that?
Apurva, ma'am.
Okay. H2 is more general than H1, and H3 is more general than H1. Sorry. H2 is more general. Yeah. And H3 is more general than H2. H2 is more general than H3. Did I make it correct?
Yes, ma'am.
Yeah. Okay, so these are the two expressions I can write here. Now see this hypothesis space H. From H2, whatever instance satisfies H1 is previously satisfied by H2 also. Did you understand this? And whatever instance is satisfied by H3 is satisfied by H2 before itself, because H2 is more general. We can represent like this in the hypothesis space. H2 is more general than H1. H2 is more general than H3. So if you take the scaling, all the down hypotheses in this hypothesis space are more general, and all the upcoming hypotheses are more specific. Okay, so we are trying to go from general to specific ordering. Did you understand? Now, is there any relationship between H1 and H3? Can you develop any relationship between H1 and H3? H1 itself is specific. H3 itself is also specific, which can be generalized from which can be specified from H2, but there is no specific relationship between H1 and H3, though there this value is coinciding. Means for H1 and H3, though sunny is same, they are not same with other attributes value. That is why they do not coincide. these two hypotheses will not coincide because there is specific requirement associated with those hypotheses, H1 and H3. Okay, so from all this, what you understood, H2 is more general than H1 and H2 is more general than H3, but H1 and H3 are not related because there are some specific requirements associated with those hypotheses. Got it? Now we'll stop here before starting this finders algorithm because I want one complete class to make you understand this. It is very simple, like playing a game. I'll just give you a brief introduction so that we'll quickly get into the concept tomorrow. We'll actually start with more specific hypothesis here. Means he is not comfortable with any of the climatic conditions. Okay, that is the most specific hypothesis. Now you start with the instances. First day's temperature are varying, means not equal to pi. There are some conditions available for the attributes. So we can understand that your initial hypothesis is too much specific, which doesn't predict anything positive. Okay, so in the next step, we'll try to make it more general. Okay, how to make it more general? By taking sunny, warm, normal, strong, warm, and same in the place of pi. Now you have encountered one instance, that is day 1, and for that day 1 you have made a hypothesis, and for that the machine has predicted it as S. The label is S. Okay, now it comes across the second instance. In second instance, sunny, warm, strong, warm, same. All the attribute values are varying, but all the attribute values are the same, but humidity value is varying. Did you notice? Means it is coming across another set of instances, another instance where the humidity is changing and all other attributes are okay. And the label is also S. It pertains to a positive label. So we have to make our hypothesis more generic. How to make it more general? By just putting question mark in place of humidity's value. So sunny, warm are the same for these 2 days. Strong, warm, and same are also same. That attribute values are also same for these 2 days. But only humidity value is changing. So you have to generalize your hypothesis by putting question mark. Means any value is allowed for humidity attribute. Okay. Now go to the next step again. In the next step, there is a negative example. Means you're not interested in this example. Machine learning model is not interested in the negative examples because machine learning algorithm is always interested in concept learning, which is the positive example. So it is not interested in any of the negative examples. So immediately when it comes across rainy, which has not been encountered so far, cold, which has not been encountered so far, and also the outcome label is no, the model is not interested to learn that instance. So do not make any change in the third step. You keep your previous hypothesis as it is. Okay, now come to the fourth example, fourth instance. Now sunny, warm are the same as first and second days. Even humidity is also the same as high. Strong is also the same, but water temperature now is varying. Okay, so you have to go for a more general hypothesis. So what you do is put a question mark in that place. Even the forecast is changing. So put a question mark in that place. So what you're doing, you're making your hypothesis more general from more specific. Okay, so you have question mark. For this you have sunny, for this you have warm, for humidity you have a question mark, for water you have question mark, for wind Yeah, for wind you don't have question mark because it is same value that is repeating. For water you have question mark, and for forecast you have question mark, indicating that it covered now 3 training examples. 3 training examples where sunny, warm and strong are common, but values are differing for humidity, water and forecast. That is why we have given a more general description there by giving a question mark. This is the final hypothesis which can apply for the given training examples in our simple example of enjoying the sport. Okay, this is how the Finders algorithm will help the machine to arrive at a generic hypothesis. Did you understand? This I'll elaborate properly, or I'll take more time to elaborate on this in the next class so that you'll understand more better. Okay. Now tell me, what is more specific hypothesis? 2 questions for you. Three questions today. Tell me, what is more specific hypothesis?
And the conditions are more, ma'am.
When the conditions are more. Very good. When the conditions are more, or mathematically you can represent that you are not convinced by any value. You have lots of preferences. You are not convinced by any value. In that case, all will be pi. That is the most specific hypothesis. Now, can you tell me the more general hypothesis?
When there is no conditions.
The condition is less.
There is no condition. I am
Any value can be accepted.
Yeah, I'm okay with any type of value. This is called as more general hypothesis. Okay. Now, can anybody explain what is inductive learning? What is inductive learning? Or any example for inductive learning? So that I can go back and explain. I can give the definition for you. What is inductive learning? All these terms you should be very familiar with. Otherwise, when you're reading about some concepts or articles on internet related to this data science or machine learning, you will again fall into doubt. What is this induction? What is this hypothesis? No, you should be very familiar with all these topics. What is inductive learning? Learning from the previous observations and trying to apply that knowledge for the future learning, for the future predictions. Okay, you're doing inductive learning, right? All the students are doing inductive learning. You're learning from the training provided by the teacher, and you are trying to apply that learning or experience in your exams. When some unseen questions are asked, that is called as inductive learning. Machine is learning from the observations, machine is learning from the training examples, and it is trying to predict something or apply its knowledge to predict something in future, which it has not seen so far. On the examples it has not seen so far. This is called as inductive learning. Now, given example of 2 hypotheses, give example of 2 hypotheses, one more general than or equal to other. Now I have given you an example of food, about making hypothesis about food. I want food which is sweet as well as healthy, and I want food which is only sweet. I'm not bothered about its healthiness. Okay, so in that case, sweet and healthy is my specific hypothesis and sweet is my general hypothesis. Now, can you give me such example? Students, I'm recruiting some employees for a project. Now I want them to be specialized in C++ as well as in Java. That is my more specific hypothesis. If I say I want them to be specialized only in Java, it is enough. Okay, let any other skills be there, but I want him to be specialized only in Java. Means if he knows Java, he would have known C++ also, right? So that is my more general hypothesis. I'm specific about one particular skill. I'm specific about two particular skills. Then I say my hypothesis, my requirement is too much specific. But when I say my requirement is only this much, not many skills are required, means I'm more generic about the requirement. My hypothesis is very general. Okay. So let's meet in the next class with more elaboration on this finders algorithm. Any doubts still here?
No, ma'am.
Okay, let's meet in the next class. Bye.